Hey peeps, welcome back once again. So in this lecture we'll try to deal with intrinsic carrier concentrations. Now to start off with, the word intrinsic means pure, right? So let's say that I have a silicon crystal. So this is a silicon crystal, and let's say this is a very pure silicon crystal. Now we'll see why we call it as a pure silicon crystal in the coming videos, because there are methods to make this unpure, and we'll also deal with that. It's called doping. But let's say that I have pure silicon for the time being. Now, as you know, that at some temperature T, let's draw my conduction band and valence band. So this is my conduction band and this is my valence band. So at some temperature T, we know that there are holes in the conduction band and electrons in the valence band. So now the point here is, let's quantify things here. So let's say that I call N0, let's say P0. Okay, let's say that I call P0 as the number of holes. Okay, so what is P0? The number of holes per unit volume. Okay, and let's call N0 to be the number of electrons per unit volume, right, at some temperature T. Now, since I have taken the case of intrinsic or pure semiconductor or pure silicon, we know that these are my pure concentrations, right? So these are the concentration of holes and electrons when your semiconductor is pure. So we'll call these concentrations a different name, which is called intrinsic concentration. Okay, concentration, and we'll denote this by Ni, right? So and one more key point to note here is that in the case of an intrinsic semiconductor at some temperature T, we know that the number of holes and number of electrons are equal. So this N0 is actually equal to P0, and since uh, these are all equal to my Ni, because I call the concentrations as my intrinsic concentration. Okay, this is by definition. This is by definition, right? So we have the equation N0 equal to P0 equal to Ni. Now, one key concept here is, how can I increase the concentrations, right? So definitely I have assumed a case of a temperature T, right? So if I increase the temperature, definitely you have more electron hole pairs generation, right? So this concentration of electrons P0, N0 and Ni, all these are going to change. Now if I look at a change of temperature, right? So I can write this expression to be, my Ni is equal to root of a t power 3 by 2 e power minus eg by kt, by 2 kt, okay, by 2 kt. So this is the expression. So where a is actually my material constant, it depends upon the material, right? So the number of holes and number of electrons definitely depends upon material. Here I have taken silicon. If I take some other semiconductor like germanium, it will be different. Now the next is T, which is temperature. Now Eg is my this gap, okay, the forbidden energy gap, and definitely KT is something that we know, which is my Boltzmann's constant times the temperature. So definitely you can see here that if I increase my temperature, definitely Ni will increase. And definitely from the above expression, you can write this to be equal to B0 and this is equal to N0. So the final takeaway from this video is that in the case of a pure semiconductor, let's say pure silicon at some temperature T, it will have concentration per unit volume of P0 and N0. And since I have taken the intrinsic silicon, you can equate this to the intrinsic concentration, right? So we call it as the intrinsic concentration, and this N0 equal to P0 equal to Ni is the equation. And this basically depends only on temperature. So if I have a pure silicon, then the number of holes and number of electrons in this particular silicon depends only on temperature and the material, and definitely this is my Ni. So that's it for this video. Hope you have understood, and let's see in the next video.